Okay, hello. First, I want to thank the organizers for setting up this meeting. For me, this is a first approximation to this machine learning quantum computing techniques, and so I'm grateful for that, and also for no, just okay, okay. Okay, maybe it's next vision. No, I said I want to thank the organizers for setting up this meeting. Because for me it was the first approximation to these topics of machine learning and quantum computing, and now also for having the opportunity to present you what we have been doing during the last time on hydrogen storage and production at the nanoscale, and to motivate a discussion about how these techniques can be applied to this subject. So let me first introduce you the problem. So hydrogen is a renewable and environmentally friendly energy carrier. Also, there are two main roadblocks for its large-scale commercial exploitation. On the one hand, there has passed 50 years from the first work on water decomposition using sunlight. And during all this time, so the dream of producing hydrogen driven only by sunlight. Maybe I can speak louder. And this one is how it works. Good. And then I have to put. Oh, it's better now, or? So there are two main problems that we have to surpass in order to hydrogen be viable as a commercial fuel. One is the production from green sources. I mean, I have said that it has passed 50 years since the discovery of the production of hydrogen by water decomposition using sunlight, but now it's still okay. So. Okay, let's try. So it's still the efficiency of the water decomposition using sunlight is too low so far for commercial purposes. And also, if you want to try to use some catalyzers, then the material costs are simply too high. So they're prohibitively high. And among the difficulties of hydrogen production, we will focus on how to make the reaction quicker. So this is limited by the so-called oxygen evolution reaction. So we have the splitting of water in oxygen, and there's one proton released into the photoelectrochemical cell that travels to the cathode. And this is the slowest process, so rate determining step. And then we are trying to investigate how to improve this to speed up the water decomposition reaction and to make this process energetically more favorable. So then regarding hydrogen storage, let me summarize the problems in this way. We need about 4 kilograms of hydrogen to give cars, for example, an independency of 500 kilometers. So they can travel without visiting the gas station. And to store this hydrogen at ambient pressure and temperature, you need a tank that is bigger than the car. So you can think about compressing it, But then, since it's a highly inflammable gas that will be subject to mechanical stress, to heating, then you need, for example, a container with very thick metal walls, and then you can really downsize to the size, size. But then, because of the thickness of the tank walls, then this tank will be heavier than the whole car, the rest of the car. So there's a problem, and what we need to achieve is a way to store hydrogen in a safe way, at high densities and with low weight of the structure. This is usually summarized in a set of goals. It's usually the references those of the Department of Energy of US. And there are several targets. I will focus on these two, which is the volumetric capacities, essentially the density of hydrogen that you are capable to absorb in a given material, and the gravimetric capacities, how much it represents the absorbed hydrogen with respect to overall weight of the hydrogen plus the container. So this more or less the two subjects I will try to summarize. And so the talk is, the outline is very simple mind. I will give you a few examples of hydrogen storage and of the calculations of the water decomposition reaction, and then I will get into the conclusions. So the idea, the problem, pictorially, the problem of hydrogen storage we want to solve is this. We have a gas that is a certain pressure and temperature that fix the chemical potential, and we want to know, given a structure with certain chemical composition and geometry, how much hydrogen molecules would get in. We want to work in the high density regime, so we expect to have many hydrogen molecules, and also because of the confinement imposed by the nanostructure, this may trigger quantum effects. So we need a theoretical framework that is capable to account for many body quantum effects. So for that, we set up a density functional scheme that is now not for the electrons, but for the hydrogen molecules treated as bosons. It's very similar to electronic DFT, but the main difference is that we have now a functional that is not the energy, but the ground potential, because we're working in the grand canonical ensemble. We'll minimize this potential, and we arrive with an equation that can be seen to be equivalent to that of a non-interacting fluid moving in this effective potential. Let me note in passing that this is different from the standard liquid DFT calculations, in the sense that usually in liquid DFT, the one used for atomic or molecular fluids, most authors try to model this term, to include, write down this as casted in an explicit form, explicit dependence on the density. But here we are following more a Comchan-like scheme, so treating the kinetic energy effects exactly by setting up the Hamiltonian for this effective reference fluid moving on the effective potential energy surface. So we have, I mean, the summaries, we have an original many-body quantum problem, and we translate into a three-dimensional problem moving in an effective potential that somehow reflects or resembles the effect of the rest of the molecules. And then we have the Bose-Einstein distribution and all the observables computed from traces of this operator. The excess energy functional, which is the equivalent of the exchange correlation functional in electronic DFT, is derived from the empirical equation of state for the homogeneous hydrogen fluid from the empirical data. So from the technical point of view, if you try to write down this Hamiltonian using, for example, plane waves, then you have a full matrix. In order to have convergent results, you need a matrix that to store you need for normal nanostructures, it can go up to 100 gigabytes. So, and then you need potentially more memory to handle to diagonalize this matrix to get the eigenvalues. So this is not possible from practical point of view. And what we do is to choose a representation that is very sparse. And we also want to the representation to be universal. So we can, for certain cases, maybe we can design a basis set that is very convenient, that is optimized for a specific problem, and that can reduce the size of the basis set. But this is not the case if we want to have a theoretical tool that is capable to predict the hydrogen storage capacity of any nanostructure. So we switch to this finite difference representation, which is very sparse, has only 7 non-zero elements in each row. And the problem we have is that these 7 non-zero elements are distributed everywhere on our matrix. Most techniques that are in the literature to deal with the sparse matrices assume certain distribution of these non-zero values. And this is not the case here. So we have the scheme relies on very heavy computational implementation because we have to define new data types and implement all the linear algebra operations on this with these special objects. And in principle, the result is that I will show you a few examples that we can compute the hydrogen storage capacities and the density distributions of the hydrogen molecules inside quite a wide range of temperature and pressures, and at least in the whole range of thermodynamic conditions that are for interest for the purpose of hydrogen storage applications. So this is an example I took as a test case, the case of carbon phones, that are these structures that you see on the left, these honeycomb-like lattices, which are named based on classifying in terms of how they are arranged, the carbon atoms on the edge of the channels, and also on the number of benzene-like rings that has each of the pores. So, and you see, for example, the things we can compute within this quantum liquid DFT scheme, and compute the thermodynamic properties. Here, this is the binding free energy, so the difference between the free energy of the absorbed molecule with respect to those in the gas phase. And you can see, for example, how it changed with respect to the size of the pores and the temperature of the external gas. You can compute the equilibrium, so the reaction constant, so the ratio between the absorbed and dissolved molecules as a function of thermodynamic conditions, the temperature of the pressure. And that gives you, for example, which is the given nanostructure, if you want to store hydrogen, which is the optimal operation point. Which is the point that it's more convenient in order to absorb more hydrogen. And then you have the quantities I told you before. This is a volumetric capacity. I don't see the point here. So the amount of hydrogen that can be stored at different temperatures as a function of the external gas pressure. And you have also the gravimetric capacity. So how much it represents this hydrogen absorbed with respect to the total weight of the structure in the low or the high pressure regimes. So you can, the idea is that you can do these calculations, and if you have a reliable model of the nanostructure, in principle exact for the cases where you attain numerical conversions, and then you can predict quantities that are of interest from the engineering or technological point of view. You can also compute the hydrogen density. Sometimes it's also important because if there's, for example, there are certain structures where you have nearly constant density along the channel walls, that means the motion of hydrogen molecules is almost free in this direction. And this is also important to, for example, to facilitate the process of loading on extracting the hydrogen that will be stored in the devices based on these nanomaterials. So this is there are several examples here of calculations carried out for carbon nanostructures. Carbonaceous materials, they are important, even if we know that more complex materials with more complex chemical compositions can store more hydrogen. These are important because we can use them to learn how it depends on different parameters like the specific surface area or the size or the shape of the pores, how it depends on these quantities, the storage capacity, and then we can use this to try to design hydrogen storage media with using more complex materials. And in principle, the scheme is very successful for these carbonaceous materials. We have addressed several nanostructures, and then we can predict, as I told you, both the thermodynamic properties and the microscopic structure of the absorbed fluid. And whenever there is a reference, either theoretical or experimental, it matches what is known at the moment. And there are also predictions for systems which are out of reach for other techniques like path interval Monte Carlo. I want also to give you a glimpse of what happens if we use non-carbonaceous materials. This is, for example, a graphene-like sheet that is composed of zinc and oxygen atoms alternating, and then the change in chemical composition what amounts to increasing the binding energy by 50%. So in principle, you can also compute the densities to know where are the main absorption sites, to localize them, to try to rationalize the absorption process. This is the gravimetric capacity. Here I present two things. On the left is the gravimetric capacity as I have shown you before. And on the right, you have what is called excess gravimetric capacity. That is the capacity, the amount of hydrogen that you have absorbed, but subtracting how much hydrogen there will be in an empty tank without the nanostructure. And you'll see that at some point, the structure starts to be problematic, counterproductive instead of helping to absorb more hydrogen, because you have completely filled the main absorption sites, and then you have some avoided space that you cannot use because it's too close to the walls where the interaction potential is highly repulsive. And then you can know also, as I told you, at a given temperature that you want to work, which is the optimal, for example, external gas pressure that allows you to take fully advantage of the presence of this absorbing material. And then we have also used run calculations for more complex materials like metal organic frameworks that can absorb significantly higher quantities of hydrogen. Then I will switch now to the hydrogen production. It will be much shorter. And the idea we have followed here is that we have a surface of the anode, because we will be focusing on the oxygen evolution reaction, what happens in the anode of the electrochemical cell. And then in principle, what we do is that we choose a part of the structure, a representative fragment of the structure, and we impose pre-boundary conditions. In the sense we can treat this as building blocks so you can generate the structure by replicating in all directions. And then we consider the approaching of water molecule, and we try different paths, compute the energy with DFT, and try to understand which is how effective is this material as a catalyzer for the water decomposition reaction. If we don't apply any voltage, or we don't have an energy supplied by, for example, by sunlight, this energy path is always uphill. You never get so it will never happen spontaneously. And then there's a minimal energy that you have to give to the system in order for the water splitting reaction to proceed. And what is usually an indicator of how effective is a catalyzer, has the catalyzing efficiency, is what is called the overpotential. It's the key figure here. That is how much energy you have to give to the system on top of this minimum that is required at ambient conditions. So as I told you, you have several paths here. You have DFT computed energies complemented by a thermodynamic model to include the external potential. And I will go directly. So the idea, the overpotential is we compute with the minimum external potential we have to apply, the potential bias we have to apply to make this free energy path downhill. So when you apply this potential from there, it's energetically favorable to split these hydrogen molecules in oxygen plus an electron that will go through the external circuit to the cathode, and one proton that will be released into the cell. So you have 4 successive proton emissions before completing the water decomposition step. So we start from the cluster model that was used before in the literature. So you see that the predicted or potentials are on top. You will have used monomer and dimeric structures, and they both predict over potentials which are over 3 electron volts. And this is very far from the experimental predictions for the two main morphologies of the titanium dioxide surface. That is the one we are addressing here. These are the experimental values for the rutile and the anatized surfaces. And then we tried to consider different cluster models in order there's one question we want to answer here, which is the cluster which better represents electronic structure and therefore the photocatalytic efficiency of a given material, and what we can learn about not quantitatively but qualitatively about this efficiency, how it changed, for example, by changing the morphology or changing the chemical composition of the material from these cluster models. And the motivation is clearly that for cluster models, you can a higher level of theory, you can describe it more precisely, and then in principle, if well, it could be, you can explore more possible reaction paths, determine, identify which is the reaction limiting, rate limiting step, and the energy barriers more accurately. So we treat, for example, adding hydrogen atoms to saturate the bonds, and then you see that it goes down to 1/2 of the previous models that have been used, the cluster model. Even for the simpler one, we consider dimeric models. I won't spend too much time here. I just want to tell you that it still is not quantitative, but for example, you can predict with this with relatively small clusters, you can already predict that the outperforming of the rutile variant with respect to the anatase variant of the titanium dioxide. So you can get the same trends like in the experiment, although you cannot reproduce the numbers. And there is a similar representation of these cluster models. And here, for example, this is the pure system, and then we start to change to dope the system with other transition metals, and was not always performing well, but at least for this heavier transition metals, you get the result that was an experimental result that is not for extended surfaces, but for nanoparticles that is nearly independent of the chemical element that you use to use titanium on the surface. So the take-home message is that you can has a more to explore a larger variety of reaction paths, so you can really see all the available phase space, because you are able to, so the higher level of post-Hartree-Fock calculations are affordable for these small clusters, and you can get some insight of how they change the trends by changing the structure or the chemical composition of the surface. We also treat, for example, I studied what is the effect of having trapped localized electronic states on the surface that we found that is counterproductive for the catalytic efficiency of the surface. So you can get some information that, again, is in agreement with qualitatively with experimental trends observed. So I will skip the conclusions. The main idea here is that, well, for the two problems I have presented you, we have a candidate material with certain chemical composition and structure. We have a theoretical method that combines quantum mechanics and statistical mechanics, and you get out as a result of the calculation a prediction for the efficiency of the material for the target application, as accurate as possible, as realistic as possible. You see that this is different from the case of the hydrogen storage than for the hydrogen production. And then based on what I have seen during the previous weeks of this meeting, I would say that there are, well, I'm listed a few hopes of how machine learning and quantum computing could be used for this topic. The first is it's very slim probability that this may be achieved to have a better or an exchange excess density function that is not so biased for the case of the homogeneous fluid. So in our calculations of hydrogen storage, we have found, for example, that many times we have noticeable quantum effects at pressure and temperatures where they are completely absent for the homogeneous fluid. So because of the confinement posed by the nanostructure. So sometimes it's desirable to have a reference that is not so biased for these homogeneous ansatz. We don't have access to that. In principle, it would be nice to have some algorithm that is capable to produce a more reliable functional, energy functional, but this is impractical in the sense that there is no sufficient reference data, reliable reference data. The dream would be that to this second point, that is provided that if we have certain parameters, like I presented before, pore size, pore geometry, specific surface area, and we get as a result of screening a very large material database, which predictions of which is the hydrogen storage capacity of these materials. Is it possible to create, for example, an algorithm that can learn how to design beforehand the better material? So how this to establish this relationship between the key parameters and the efficiency of the hydrogen storage problem. That was something that could be nice, I think. In the case of quantum computing, what I find most promising is this quantum embedding techniques that could be used either for the liquid density functional calculations, for the electronic density functional simulations of the water splitting. So with that, I would like to thank well, my collaborators are listed here again, the funding and your attention. I'm happy to take questions. Yes, I took the
May I see the slide where you show the stacking of hydrogen molecules into carbon foams?
Yes. Nice. The one. Yeah.
Yes, and those different cases also. Okay.
Different carbon nanostructures.
So in all these structures. Qu'est-ce que je dois faire? Il y a un faux contact, je pense. Il y a un faux. Okay. I wonder if one of these situations can model one.
Là devant, oui.
Okay. Is it okay? Okay. I wonder if what I want to say is at the wall of the you have the retention of tritium, and it could be tritium probably with the same thing. What is?
There will be so there are, in principle, yes and no. Or yes, it's in principle the methodology is universal. Difference is that I guess that you can only get atomic tritium or whatever hydrogen because temperature is too high.
It's about yeah, it can be also 1 electron volt, for example.
It could be, but I guess then that classical liquid DFT will be enough I guess this is completely, this is much more efficient and simpler in this case,
Okay.
because you don't have the exponential of an operator but of a function. It's like having only the diagonal terms in this function I showed you. This is much more, can be done. There's no problem, but it's a much simpler problem. And what I found problematic, I don't know, maybe it's possible, is to find a good reference to construct the excess energy functional. So you
To
need
construct what?
the excess energy functional.
Oh, okay.
So this is because of precisely of the thermodynamic conditions are so extreme that maybe they, if there exists an equation of state, then yes, the procedure is directly, straightforwardly generalizable to this situation. If there is not an empirical or a quantum Monte Carlo computed equation of state, then it's more difficult. You need another reference to incorporate these many body effects.
Okay, thank you.
And sorry, and you have also taken into account that if this is that the possibility that they bind the molecules. So this is functional for the hydrogen molecules treated as a single particle. You may also have equally at the same level of complexity one for the hydrogen atoms, but then you have to build something else if you have a mixed regime where you have both hydrogen molecules. We have worked in that. It's not impossible, but it's a different level of construction of density functional.
Okay, thanks.
I'll see you.
Any more questions? No. Okay. So thank you very much.
Thanks.
Let's thank the speaker again and all the speakers of the session. And I think now that there is a discussion session, so we can go upstairs.